can hear me all right? Yes, awesome. Okay, so hi, my name is Vincent. I'm an Android developer, and today I will take you on a journey of building a small library cross-platform. So our outline for today will be first to demonstrate why we even need a library to begin with. Second, I will try to argue the design decisions that go into making that library. I will demo a bit of the implementation, not too much because walls of code is not fun to read. And then hopefully you will have learned something new today at the end of this talk. So first, we start with strings, series of characters. We all know them, or yes. And so then let's say that we have a string like this, DevFest Montreal 2004. We can display it like this. We can bold it. We can italicize it. We can pretty much style it however you want. We can, for example, do like a bold part at the end and then just leave the rest as is. It's pretty straightforward. Let's say that we want to represent this inside of our application. Like for this example, I'm going to use Android, but it works for pretty much anywhere else. Like you just like in Android, you have what's called an annotated string with the pretty useful like builder pattern that we can use, where like we start with putting the DevFest Montreal at the beginning. That's not styles, and then we add our span for the bold part, and then we just append the rest of the string that makes it bold. So this works. We can use it today, but as we start to see some different use cases, we can see that there's some issues that rise up from this. The first one being that how do we handle resources? So let's say that I want to inline an image at the end for accessibility purposes, or for example, a wheelchair or the logo of a company. I want it to be in line with the text, or I want to dynamically load an image. It's kind of unclear how I would go about doing this without reinventing the wheel, or how to handle accessibility. Like when we start to build these kind of complex styling structures, we start to run into issues with consistency of accessibility. Like where would the screen reader even look? Then you have user preferences. Like every device, the user will set up various things like their time zone, or like if they want, for example, 24-hour versus 12-hour displays. And so how do we handle all of these different combination of user preferences? And the same thing with dynamic strings. Basically, in the real world, strings display information, and that information changes a lot depending on the context where we see that information and what the information we're trying to display. And so if we're hand building all those strings by hand, we run into issues almost immediately. So the solution to all of these issues is to build our own library, which will handle these use cases. So let's say that we have an application that has multiple different building targets. So we have an iOS app, an Android app, some sort of web target, and we try to handle most of the code we can inside of a common code area. Using this particular framework, I think one of the first things that we should be doing when we start to write our own library is to set some few design guidelines straight off the bat. This allows us to better inform our design decision making and like the different trade-offs that go into engineering a library. So for a particular use case, we would see that, well, we have multiple platforms, and so one of the first design guidelines that we should strive for is to avoid code duplication between platforms. So it's pretty straightforward. And then the second one would be to make it easy to extend and be flexible, because our rendering would the information that we want to render will change over time depending on our business cases, and so we want to make sure that our library is flexible enough to handle future requirements. The third one is to minimize the API surface. That part is more important for the ergonomics of consuming the API. If we make things way too complex or have many different ways of integrating the library, then we can run into issues in the long term, because every way to integrate the library is a way that you have to support in the long term. And so you're duplicating your support burden when you have a very large API surface. And the fourth one is performance. I won't touch much about performance during the talk, because it's something that can obscure a bit more of one of the things I'm trying to do, trying to present, and makes it a bit difficult to understand, but I will circle back on the performance towards the end to point where we could make the library more performant. So if we go for this first point, the avoid code duplication between platforms, if we look at the diagram, one thing that for me jumps straight ahead is that we have this common code area. And when we try to share code, one of the tools that I like to reach for is Kotlin Multiplatform. So sorry for all the Flutter people in the audience. So one of the reasons why I find that Kotlin Multiplatform, well, first of all, how many people are familiar with the Kotlin Multiplatform? So, okay, so since it's about half of the room, Kotlin Multiplatform, for those who don't know, is a framework used to share code between platforms. And it's very nice for multiple reasons. The first one is that it's written in Kotlin, so you can have all the great ergonomics of the Kotlin language, which is it's a joy to write in. Second one is that it allows for incremental adoption. Since we're working with an existing application, having incremental adoption is great because it allows us to have small experiments, add over time, and minimize the risk of a full rewrite, for example, in order to take advantage of this. And the third one is that it allows for a flexible API boundary. And particularly that last point, flexible API boundary, is something I want to dive into deeper. So if we go back to this diagram, I like to understand Kotlin Multiplatform, or KMP for short, as a sort of line. So I call it like the KMP line. And this line would mean that everything that's on the left of this line would be common code, common platform code that can be shared between all of our building targets. So in this particular case, for example, our code is limited to library code. And we can even add an external source to this. So we could have even Kotlin on the server that shares code with our library code. But then when it becomes very nice is that you can move this line around. So if I move this line to the right, what this would mean is that our entire application from start to finish is common code. And so even on the platform level, through, for example, Compose Multiplatform developed by JetBrains. But if we don't want to go all the way, you can also go maybe halfway. Maybe part of my screen is Kotlin Multiplatform, but then the rest of the screen is native rendering, native UI. In our particular use case, since we already have existing native code, I will focus on making a sort of library that sits in the middle and that feeds in data to the already existing native targets. So that takes care of the first point, which is avoiding code duplication. And then when we go on to talk about the next 2 points, this is where our implementation will come into play. So basically what we're trying to do is we're trying to present a sort of how do you call it? We're trying to present a representation of the structure of our styling, our metadata, and our content for our strings. And so in order to accomplish this, we kind of want to do it through a language that allows us to express those particular things. And so the language that we could choose, for example, we could go with JSON. JSON allows us to have a sort of representation where we could have like various menus with like various lists where we could list the style of our strings, we could list the different component resources, etc. So it works great because it's very flexible. You can put pretty much anything you want inside of a JSON. But since you can put anything you want inside of a JSON, it's almost too flexible in the sense that you will run into issues when it comes to typing, where like you have to do a lot of tooling in order for that to happen, or you don't have guaranteed ordering, and so it becomes really critical when it comes to styling to be able to have a guaranteed ordering. You can jerry-rig it into a JSON, but then you end up with quite a bit of overhead, and that's not really desirable when it comes to just rendering strings. It's something that should be performant and pretty quick. So then you take a look at, for example, HTML, where this works great because it already has a markup language. So you can see you have the H1, you have the P, you can do strong. So it already has the structure that we want to stylize those strings, except that with HTML, what you're going to find is that there's like 5 different ways to do pretty much anything. So if I want to bold some kind of text, I can use a strong tag, but I can also use a span with a style. I can do all these different ways. And then because there's all these different ways to do it, as a library, you have to support all these ways because you can't know in advance what the consumer will consume. And so it creates this huge support burden for all of the different ways. Not only that, but also you're going to find that there is like a lot of different tags, and you don't need even half of those if you want to display strings. And so the solution we land on is to design our own language. So this is what's called a domain-specific language. And so, for example, if we have a bus schedule item where like we have a stop, we have the name of the bus schedule, and then we have some sort of maybe ATA. So how we would represent this using our own language would be to, well, inspired by XML like HTML, we could do like a bold tag at the beginning for the stop, which is pretty straightforward and what you're used to. But then for the ETA, we could do something like an ETA tag that we make ourselves with any kind of parameter. For example, in this case, we put the late because probably maybe the bus is late and we want to have like a particular rendering color for that use case that's proper to our business. This is pretty good because it's minimal. We only have the part of the language that we need. It's flexible and accessible because we control the keywords that we can use. We can extend it with any new keywords that is required for a business. Because we control the keywords, we can have it typed the entire way, and we can share those types between platforms. And we can also make it more performant because we control the entire thing. I will touch back on the performance, like I said before. So for example, what kind of keywords we could use? We could pretty much put anything we want. So if we have a banking app, it could be about currency, or about if we have something like a transportation app, then it could be like a stop, like branch codes, numbers. It could be even stuff like countdown, so that we can display a countdown inline that animates over time. So what it would look like inside of our application would be that we get some sort of string with this particular serialization format. We pass it through our library. Our library transforms it into a format that can be easily consumed by the native renderer of each of our platforms. So for example, in this case, the Android one in the middle has like a user preference for 24 hour, and so it would display differently compared to another platform. Something that we couldn't really do on if you were using HTML, for example. So since we're taking some sort of string, we're passing it, and then we're converting it into something that's useful, we're kind of building a compiler. But we're not building the entire compiler, we're just building the parser part of the compiler, because a compiler takes source code and then converts it into machine code that can be executed. In our case, we don't really care about the whole process. All we want is the parser, which is in charge of the syntactic analysis of the string and adding structure to it. So what would it look like if we try to implement this string parser? It would look like something like this. We have an input that goes into a lexer, which then parses it into tokens, which are then fed into a parser, which produces an AST tree that we expose to a renderer. Since I said that the renderer stays native on the platform, our library will focus on taking those input strings and producing an AST tree out of it. So a lexer, which is the first part of the process, is basically what's called a tokenizer or a scanner. It takes the raw input and tries to tokenize it into syntactically significant tokens. So for example, if we have a string like this, if we try to break it down, we have the bold tag at the beginning, we have some content in the middle, we have a close tag, after that we have more content, we have an open tag but no close tag yet, which is the ATA, we have a vertical line separator, we have some sort of parameter, followed by another line separator, a second parameter, and then a close tag. So if we try to reason about the structure of this, our tokens kind of look like this. We have a name slash parameter with some content in the middle. So if we formalize those tokens, they would look something like this. We would have like a tag begin with a name. We'd have a tag end that's just the closing bracket. A tag close, that is the closed tag. We have parameters, which is anything between the vertical separators, and our content, which is anything that's between the tags or at the beginning or the end. And so what it would look so now I'm going to try to show some bit of code just to ground this theory. You don't have to pay too much attention to it. It's more just to kind of show how it would work in practice. So the first one is like we would have, for example, a token class, which has all of our different tokens with like different information that's useful. For example, we have the name of the tokens for the tag begin. And one thing I want to bring your attention to here is the position element that we keep. When we're doing any sort of parsing, keeping track of the position of the different element is very, very useful during the process. So you'll see why later, but so it's an element that's important. So then when we're building our lexer class, it's pretty straightforward. We just have a function that produces token. This function goes through all of the characters in the current string, and then if it hits an open bracket, then you kind of go into the read tag part of your scanning. And if you don't, as long as you don't hit that open bracket, you're reading content. And so those are the two different parts that you see here, if or else. Then for the read content, it's pretty simple. It's just, well, add anything that you see into the content. But then for the yes, so unless you hit a square bracket, then you go back into the read tag. So when you go to the read tag, you start with reading the name, and then you add that, and then if you hit a slash, you're now in the tag close, so you're just done. Else, you read the name, yes, okay, and then once if you're not hitting a slash, then you're into parsing the actual tag. So the tag has a name, and then if sometimes you hit a parameter, so this is delimited with the vertical bar, and then if you hit that bar, then it means that you're inside of a parameter. So you do basically the same thing. You parse until you hit another bracket, then you return. So then for reading the name, it's pretty much the same thing. You just as long as I have letters or digit, I just scan it. One thing I want to bring your attention to is the parsing exception. So we'll see this in the next one, which is that one of the things that you should do at the beginning of building any sort of parser is that you need exceptions. Because otherwise it becomes very, very difficult to debug. So by using exceptions like this, you can, by just setting up an exception that returns the position of where the error is, it means that if while you're coding it, if you hit something that's you're not supposed to hit, you can know immediately where your error is. For example, in this particular case, we know, for example, oh, he was expecting a close bracket, but it missed it, and so it's at this position as well. So it makes it very easy to, it makes it much easier to iterate over time when you have clear error messages in your code. So I highly recommend to put them in if you're trying to do something like this. So in the end of the day, after all this code, we ended up with this kind of result to the right. So let's say that we have a string with like a hello with like a bold, a parameter 1, a parameter 2, and then a closed tag. We'd have something like this. We have a list of tokens that are like content, tag begin, parameter, with the various information and their position in the string. This doesn't have any structure. It's just a raw token of just a raw token list. To have the structure, this is where the parser comes in. So the parser this job of the parser is to add structure to the list of tokens that we just passed through. And it does this by first validating the syntax and outputting what the most important for us, an abstract syntax tree, which I will go into it a bit later. So in order for us to validate the syntax of our language, I need to briefly talk about grammar. It's not a compiler class, so I'm not going to go deep into grammars and all that kind of stuff. But it's important because it allows us to have a bit of a theoretical grounding for what we're trying to do. In particular, there's a bit of vocabulary that's useful for us, which is that in grammars you can classify symbols into various types. One is terminal, which would be like the leaf of our tree. So it would be text, image, date. Like there's nothing after date. The date is just an object that is. So like the content, for example, is also terminal. Then we have non-terminals, which would be more like our styling nodes. So they would be bold, light, flashing, is it marquee where it goes around the screen, and then start symbol is just the beginning of our whole chain. Using this grammar, what you will often see in compiler theory is what's called like production rules, which is a very fancy way to just say, well, what are the rules for replacing every non-terminal? So it's basically the structure, the syntactic structure of our language, which means, for example, a non-terminal can be replaced by a terminal and another non-terminal. So that would be kind of the format it would take. Like, for example, on the right, you have maybe a bit more visualization, a bit better visualization of what it would look like for JSON, for example, where like you have an open bracket, it can either be a white space and a closed bracket, and then we've hit the terminal, and so it's done. Or we can have like a white space, a string, a white space. You see the deal, and then you come back. So in our case, it's not really useful to formalize the whole language like this because it's pretty simple. It's a bunch of XML tags for the most part. And so we don't really need to do this, but just so you know that there exist many tools online where they will take the production rules and generate a parser for you. So you don't have to write the parser by hand. You can just use those rules. In our case, we can write it by hand because it's pretty simple. I'm not going to show much of that code because it's pretty much the exact same logic that we did for the tokenizer, where we have a statement depending on the state that we're in. So the goal of this at the end is to generate what's called an AST, or abstract syntax tree. This is basically the syntactic representation of our code. And a good way to visualize this is with like embedding our two tags together like this. So we see that all the text nodes, which are terminals, are the leaves of our tree, and the non-terminals end up being inside of our tree like this, having children. So, for example, we have like hello, bold, world, a word with a color, a parameter for the color, a time, and then like two closing tags. So what it means is that if you look at it, you have the first text, which would be the hello. Then you could go down the tree on the bold, and then you have a text and a color and a text. So the text would inherit basically the color and the bold. So it would look like in code is something like this, where we have like a string element, we have like a text element, which is just the content, and then a bold element that can contain more string elements. So just sort of to organize a sort of tree. So this would take care of the parsing part of our little library. And now we go to the renderer. But when we go to the renderer, we realize that it's basically this is where our API is. So this is where our library will interface with the consumer. And we will run into issues if we expose the AST directly to the consumer. It's something that you never want to do because the AST encodes the entire syntactic structure of your language. And this means that if you expose the AST to a consumer, anytime you make any sort of change to your language, you will immediately break all your consumers. So you need to define an API that will allow the consumer to interact with that tree without having to actually directly access the tree, which is the third point, which is minimizing the API surface in order for us to prevent breakage. So in this case, what we can do is we can walk the tree for the consumer, which means that we would walk the tree in order to expose an ordered list of styled elements to the consumer, which then the renderer can plug into and render on each platform. So if we take a look at how we would go about doing this, you would start at the root, you would visit the first tech nodes. I think that's an in order traversal, if I'm not mistaken. There you go through the text node, and then you don't have any more children, so you go back to the root and you go to the bold, followed by the text. So that text is bold. Then you go to the color, and then so that text takes the style bold and color. So how we would expose that how we would define this in code for our library. In our common code, we would have a parse style text that returns a list of style elements where we do all of the different steps that I showed before. So we would lex the tokens, we would parse into our AST tree, and then we would flatten that AST tree into a consumable style list. And then, for example, this is for the Android part of it, we would have a composable that just takes an input string and then parses that style string, and then we have we can build the annotated string where we can just iterate over our entire list and render them depending on our rendering logic at that particular point. So that will be our entire library, but we have still more and more point to go to, which is the performance part. So I've skipped over the performance because in order to present it in a readable way, but in reality, when you're building a parser, one of the first enemies that you're going to face is memory allocation. If we see through all the code examples that I've shown, we're allocating objects left and right and passing objects all around willy-nilly. It's easy to do, but if you do this too much, you're going to end up paying a huge amount of performance cost when it comes to garbage collection. So one of the first steps that you should do when you're building a parser is to be very, very mindful of memory allocation. So this is one of the first optimization steps that you should be taking. The second one is that the best, most performant, bug-free code is no code at all. Which means that if there's something that you don't explicitly need to do or use, then you should not use it at all. Which means that, for example, since we're using strings as our serialization format, there's inherent trade-offs in terms of performance already baked into that particular process. And so it's not something that you can use everywhere that you don't need it. Like if you don't need it, don't use it. And then if you do, then that's where you're ready to pay that cost. And following this particular rule, one thing that you can see pretty easily is that since our lexer and our parser are so simple, you can pretty much, it's a pretty good idea to be combining them together. So you would parse the tokens as you're reading your characters on the list, which avoids the unnecessary step of producing tokens that you then iterate through. It's like you can pretty much do it in one step. So this would be this part here that we can combine. And then the last one is, since you're dealing with strings, sometimes strings they change, but sometimes they don't. And so when they don't change, or you do something over and over again, you can leverage caching to avoid making and doing unnecessary work. And then if we want to push things further, then there's a few more areas where you can go to. I'm not going to talk about them here, but they're pretty important to mention. The first one is that you can go 100% KMP. So right now the rendering part was left for the platform, but you can imagine a world where you bring also that part into the common code and have the rendering and like the parsing and the rendering inside of the same code base. The second one is what's called JIT, or just in time. If we go back to here, for example, you can see that we are parsing the string at the same place that we're rendering it. And so a performance optimization that we could do, if we go back here, would be to render the string as we're parsing it, since we're doing all of this at runtime. It would allow us to avoid doing like one pass of parsing and then one pass of rendering. A third one is test coverage. I didn't talk about tests here, but tests are pretty important, especially for that type of library. And the fourth one is versioning. Anytime you build your own serialization format, DSL, anything, versioning is something that's often overlooked, but your future self would be happy that your present self thought about versioning. especially down the line. So that'd be it for me. For reference, most of the examples are derived from this book called Crafting Interpreters, made by Robert Nystrom. It's a great book. I highly recommend it. If I can say so, it's a fun compiler book, which is not something I thought would exist ever. So it's great. It's available for free on the link right there. So if you want to read it, I highly recommend it. And that will be it for me. So thank you very much.